Most automotive ignition systems use an induction coil to step up the nominal battery voltage of 12 volts to the voltage needed to bridge the gap across the spark plug electrodes. These induction coils operate according to Faraday's law. Relative movement between a conductor and a magnetic field allows 4 ways by which an electromotive force, or EMF, can be induced in a conductor. Move a magnet so that the magnetic lines of force cut across a conductor, as in an alternator. Move the conductor so that it cuts across the stationary magnetic field, as in a generator. Start, stop, or change the rate of current flow in a conductor. This causes the conductor to induce an EMF into itself. This is called self-induction. Start, stop, or change the rate of current flow in a conductor which is positioned close to a second conductor. This is called mutual induction. When any of these methods is used to induce voltage in a conductor, the value of that voltage depends on the density or strength of the magnetic field. The stronger the field, the greater the induced voltage. It is also influenced by the number of turns of the coil. The greater the number of turns, the greater the induced voltage. The speed at which the lines of force are cut also affects the voltage induced. The greater the speed, the greater the induced voltage. In the induction coil, the secondary winding has many thousands of turns of fine enameled copper wire. The primary winding, with a few hundred turns of relatively heavy wire, is positioned close to the secondary. A soft iron core is positioned centrally to concentrate the magnetic field. Current flow through the primary winding establishes a magnetic field around the windings. The higher the current flow, the stronger the field. Sudden interruption of the primary current effectively disconnects the battery from the coil and current flow ceases. This leaves no externally applied voltage source to dictate the voltage value across the ends of the primary winding. The magnetic field decreases, returning its stored energy to the coil by cutting across the coil windings. This produces a self-induced voltage in the primary winding and a mutually induced voltage in the secondary winding. The maximum value of the secondary voltage is partly determined by the ratio of the number of turns in the secondary winding to the number of turns in the primary winding, in this case 100 to 1, and by the value of the self-induced voltage in the primary winding, in this case 300 volts. Then, if this coil is 100% efficient, the maximum voltage available from the secondary winding would be 300 volts multiplied by 100. That is 30,000 volts. Since the value of the self-induced voltage in the primary winding is also influenced by the rate of change of current flow through the coil, it is essential to switch the primary current off as quickly as possible. All ignition systems make provision to ensure that this occurs.
This section examines basic electricity. All questions about the nature of electricity lead to the composition of matter. All matter is made up of atoms. Every atom has a nucleus with positively charged protons and neutrons with no charge. Moving around the nucleus are negatively charged electrons. With equal numbers of protons and electrons, their charges cancel each other out, leaving the atom with no overall charge. An excess of electrons gives an atom a negative charge. A deficiency gives it a positive charge. In some materials, there are electrons called free electrons, only loosely held by the nucleus. The more free electrons a material has, the better it can conduct electricity. Metals typically have lots of free electrons and are good conductors. In insulators, electrons are bound much more tightly to the nucleus. They cannot easily move freely, so they are not readily available for electric current. Semiconductors conduct electricity more easily than insulators, but not as well as conductors. They are crucial in electronics. Free electrons are necessary for electric current, but for those electrons to move, they need a complete pathway or circuit. And there must be a force to make them move. The force here from a battery sets these free electrons moving. Like charges repel, so the negative electrons are repelled from the negative terminal. Unlike charges attract, so the electrons are also attracted towards the positive terminal. They flow in one direction only. This is called direct current, or DC. Most circuits in motor vehicles use direct current. The larger the charge at the positive terminal, the more strongly it attracts free electrons. This attraction acts as a force driving the electrons along. The greater the force, the stronger the electrical current. The force is called electromotive force, or EMF. It's also known as voltage. Also affecting the current flow in a circuit is electrical resistance, measured in ohms. All materials have resistance, even good conductors. 4 factors determine the level of resistance: type of material, whether it has enough free electrons, length of the conductor. As length increases, so does resistance. Size of the conductor. The larger the conductor, the greater the amount of current it can carry. And temperature of the conductor. The higher the temperature, the harder it is for electrons to pass through it, and the higher the resistance. While all materials have some resistance to current flow, a resistor is a component designed to cause a particular voltage drop in a circuit. It has a set resistance, usually marked or coded on its surface. Since electric current is the flow of electrons, it is natural to say the direction of current is the direction in which electrons move. However, before the discovery that electric current was the flow of electrons, it was thought the natural way for electricity to move was from positive to negative. Both concepts are still in use. Current set to flow from positive to negative is called conventional current. Current set to flow from negative to positive is called electron current. All electrical circuits in this training material will assume a conventional direction of current flow. This section examines static electricity. Static electricity can be induced by rubbing 2 insulators together. One material loses electrons to the other. The one losing electrons becomes positively charged. The other gains electrons to become negatively charged. When these 2 charged surfaces are brought close enough together, a spark may jump as electrons leap the gap to cancel out the charge imbalance. This can be experienced as an electric shock. This applies to any charged surfaces where the imbalance in charge is large enough to make the electrons leap the gap. The spark can be dangerous. Near fuel vapor, as at a service station, it can even cause an explosion. This section examines producing electrical energy from heat energy. If these 2 different metals are joined and heated, a small electric current can be generated. For a temperature rise of around 200 degrees Celsius, the potential difference created is about 9 millivolts. The point that is heated is called a hot junction, and the whole system is called a thermocouple. In developing engine designs, manufacturers use thermocouples as high-temperature indicators to determine temperatures of components such as spark plugs and exhaust systems. This section examines producing electrical energy from chemical energy. When 2 dissimilar metals are immersed in a conducting liquid called an electrolyte, the breakdown of chemicals into charged particles, called ions, results in a flow of electricity. The process is called electrolysis. It is applied in the standard lead-acid battery used in most vehicles. This section examines producing electrical energy from light energy. If light energy strikes the surface of some semiconductor materials, they emit electrons. These freed electrons can then be made to flow in a circuit. The principle is applied in some ignition systems and vehicle speed sensors. This section examines electrical energy produced from mechanical stress. When crystals of certain materials, such as quartz, are subjected to mechanical stress, it produces an electrical potential across the crystal. The process is reversible. A potential difference across the crystal will distort the crystal. This principle is used in pressure sensors in some electronic fuel injection systems. This section examines electrical energy produced from magnetic energy, also called electromagnetic induction. When a conductor cuts across a magnetic field, current flows in the conductor. It flows one way when the conductor cuts the field in one direction, then reverses as it cuts the field in the opposite direction. The current is called alternating because it flows one way and then the other. The term alternating current is often shortened to AC. That's the sort of electrical energy that comes through the power points. It's also produced by an alternator, as the name indicates. Moving a wire inside a magnetic field produces a current flow. Similarly, moving a magnet inside a stationary coil of wire produces the same effect. This magnet is rotating in an iron yoke. A coil of wire is wound around the stem of the yoke to form a complete circuit with the ammeter, which indicates if current flows. As the magnet rotates, the ammeter deflects for current flow. For every half revolution, current flow reverses. Increasing the speed of the magnet increases the amount of electrical energy produced. Electromagnetic induction is applied in alternators and ignition coils. This section examines the heating effects of electricity. As current flows through motor vehicle circuits, most of the electrical energy is transformed into other kinds of energy. Headlamps transform it into intense heat that makes the bulb filaments glow white-hot and produce light. It can demist a window, or can be used to provide circuit protection from excessive current flow. This section examines the chemical effects of electricity. Chemical effects of electricity depend on ions, electrically charged atoms or groups of atoms. If an atom or group of atoms gain electrons, they become negatively charged. If they lose electrons, they become positively charged. When two different metals are immersed in an electrolyte, one loses electrons and becomes positive. The other gains them and becomes negative. Negative ions in solution are attracted to the positive plate, and positive ions to the negative plate, and a chemical reaction can occur. In a lead-acid battery, the electrical and chemical differences between the sets of plates creates a potential difference which makes the current flow in a circuit. It flows in one direction only, so it is called direct current or DC. As electrons move from one set of plates to the other, the same compounds form on the plates. If this happens for too long, there will be no difference between the plates, and current stops, leaving a discharged battery. Of course, a battery can be recharged, so that the difference between its sets of plates is restored. This section examines magnetic effects of electric current. When current passes through a conductor, a magnetic field is created around it. When wire is wound into a coil, it produces a much stronger magnetic field. By turning current to the coil on and off, this magnetic effect can be turned into mechanical movement, pulling a switch open or closed. This is the principle behind electrical relays. Coils of wire can be mounted on a shaft and placed in a magnetic field. Sending current through the coils draws them across the field, and if the current is accurately switched, this is constantly repeated to produce the rotary motion of the electric motor. This section examines basic electronic principles. Electronics usually refers to devices where electricity is conducted through a vacuum, gas, or semiconductors. Automotive applications mostly use semiconductors such as diodes, transistors, and power transistors. Their electrical resistance is higher than that of most conductors, but lower than that of most insulators. A semiconductor's conducting ability depends on two kinds of charge carriers. The first is familiar, the negative electron. This kind of semiconductor contains an excess of free electrons. They can be made to flow and carry charge. The second type of charge carrier occurs from a loss of electrons, with gaps called holes, where the electrons were. Since negative electrons have been lost, they are called positive holes. And because they are positive, a voltage can make them move towards the negative pole. The number of charge carriers in a material can be altered by doping or adding very small quantities of impurities. A doped semiconductor always has an excess of one type of charge carrier. Electrons in excess make it an N-type semiconductor, N for negative. Holes in excess make it P-type, P for positive. When connected into a circuit, both the electrons and the holes move, and current can be thought of as moving in two directions. So electron current and conventional current are both used in electronics. Most electronic components combine P-type and N-type semiconductors. Where they join is called the P-N junction, an area where some electrons and holes cancel each other out. A thin layer forms that acts like an insulator. Since it has so few charge carriers, it is called a depletion layer. A semiconductor diode has a single P-N junction. If it is connected to a current source so that the P region is connected to a negative pole and the N region to a positive pole, the negative pole attracts the holes and the positive pole the electrons. This enlarges the depletion layer and insulated space. As a result, current cannot flow across it. If the current source is connected in reverse, holes flow in large numbers across the junction towards the negative pole, and electrons move in the opposite direction towards the positive pole. The P-N junction floods with charge carriers, the depletion layer disappears, and with it, the insulator effect. In this direction, the diode lets current flow. This principle of the P-N junction operates in most semiconductors. Semiconductor devices are replacing many other kinds of switching. They are small, light, and use low operating voltages. They're reliable, need no maintenance, and they're easy to manufacture. This section examines batteries and cells. Electrochemical cells transform chemical energy into electrical energy. There are two types, primary and secondary. In a primary cell, this transformation is not reversible, and the cell is discarded at the end of its life. In the secondary cell, the transformation is reversible, and it can be recharged. There are two types of secondary cell, wet and dry. In automotive use, the usual main storage device is the wet cell of a lead-acid battery. It has two plates of dissimilar materials immersed in an electrolyte, a solution that conducts electricity by using ions. The accepted or nominal voltage of a cell does not depend on the size of the cell. However, current capacity does. The surface area of the plates in a cell determines its current capacity. In a lead-acid battery, the plates are assembled so there is always one extra negative plate. The plates are close to each other but do not touch, which would cause a short circuit. The nominal voltage of a cell is 2 volts. Cells connected in series make a battery, and the number of cells determines its nominal voltage. The cells are sealed from each other and filled with dilute sulfuric acid. The battery case is usually plastic or hard rubber. One set of plates is connected to the negative side of a DC source, and the other to the positive side. Direct current is applied to the plates, changing them chemically until the battery is ready for service. In a discharged lead-acid cell, the active material of both plates is lead sulfate. The electrolyte is a weak sulfuric acid solution. The cell is connected to a DC source with electrical pressure higher than that of the cell, since it must act like an electron pump, forcing electrons from the positive plates to the negative plates. At the negative plates, sulfate is discharged. More sulfuric acid forms, and the plate changes into sponge lead. At the same time, lead peroxide is formed at the positive plates, which restores the cell's electrical potential. The charging process increases the amount of acid in the electrolyte, making the electrolyte stronger. When further charging no longer makes the electrolyte stronger, charging is complete. Now let's examine discharging. Connecting a lead-acid battery to a load causes chemical changes. At the positive plate, sulfate from the electrolyte joins with lead to form lead sulfate. Oxygen from the plate joins hydrogen to form water. Lead sulfate also forms at the negative plate, as sponge lead forms with sulfate from the electrolyte. Overall, the percentage of acid in the electrolyte falls, and the percentage of water rises, which reduces the strength of the electrolyte. As the cell discharges, the plates develop the same composition, which reduces the potential of the cell. This section examines Ohm's law. Voltage can vary across different points in this circuit, but measuring current at any point reveals it is always 2 amperes. This can be found without an ammeter by using Ohm's law. If resistance stays the same but voltage rises, then the greater force pushes more current through the circuit. If resistance stays the same but voltage decreases, then less current will flow through the circuit. If voltage and amperage are recorded each time they change, and each voltage is put over each amperage, the resulting fraction always equals the same number. Total resistance of a circuit in ohms always equals the voltage divided by the amperage. This is Ohm's law. R stands for resistance, V for voltage, and I for current in amperes. R equals V divided by I. Therefore, I equals V over R, and V equals I multiplied by R. This triangle is an easy way to remember them. R equals V over I equals V over R, and V equals I multiplied by R. With Ohm's law, as long as any 2 of the 3 quantities are known, the third can be calculated. Instead of breaking into a circuit to measure current with a meter, if voltage and resistance are known, Ohm's law may be used. Battery voltage can be measured, 12 volts. The value of the resistor is on its casing, 4 ohms. Current then equals voltage, 12 volts divided by resistance, 4 ohms. 3 amperes of current flows through every point in this circuit. This section examines electrical power. Energy is the potential to do work, but work is done only when the energy is released. This disconnected battery isn't doing work, but it has the potential to do work, so it's a source of energy. The difference in electron supply at the battery terminals is sometimes called the potential difference. In this case, a potential of 12 volts. Tapping this potential means turning one form of energy, the battery's electrochemical energy, into another. Turning one form of energy into another is called work. The amount of energy transformed is the amount of work done. In this example, physical energy is being turned into mechanical energy. Work is being done. Here, the same amount of work is done. The same amount of energy is transformed. in this case from electrical to mechanical, but there is a difference. The power drill is quicker. That difference is called power. Power is the rate at which work is done, the rate of transforming energy. In an electrical circuit, power refers to the rate at which electrical energy is transformed into another kind of energy. The unit of power is the watt. 1 watt is produced when 1 volt causes a current flow of 1 ampere. From this comes the power equation. P, the power in watts, equals V, the voltage in volts, multiplied by I, the current in amperes. It's applied just like Ohm's law. When current flows in this circuit, the resistor may become hot as it converts electrical energy into heat energy. By Ohm's law, 2 amperes of current are flowing in the circuit. From the power equation, a voltage of 12 volts and current of 2 amperes means 24 watts of power are being taken from the circuit by the resistor. This triangle simplifies transposing the power equation. Power equals voltage times current. Voltage equals power divided by current. And current equals power divided by voltage. This section examines series circuits. In a series circuit, current flows to each component in turn. There is only one path it can take, and all the electrons flow at the same rate. Current is the same everywhere. In this series circuit, total resistance is the sum of all of the individual resistances. 12 ohms. By Ohm's law, 1 ampere of current is flowing through the whole circuit. However, voltage at different points changes as the electromotive force or pressure drops from a potential difference of 12 volts as it leaves the battery to virtually no difference, no voltage at all, as it returns. This is called voltage drop. It is caused by the pressure lost in driving the current through the resistor. After the first resistor, voltage has dropped from 12 to 8 volts. After the second, it's down to 4 volts. After the third, 0. The voltage drop across each resistor can be found by subtracting the voltage after a resistor from the voltage before it. Or the difference can be measured. The voltmeter will read 4 volts in each case, because that's the difference between the 2 points, the potential difference or voltage. Ohm's law can be used in series circuits to calculate voltage, resistance and current. Any one can be calculated as long as the values of the other 2 are known. This section examines parallel circuits. In a series circuit, components are connected like links in a chain. If any link fails, current to all the components is cut off. In a parallel circuit, all components are connected directly to the voltage supply. If any connection or component fails in a parallel circuit, current continues to flow through the rest. This is one reason why parallel circuits are used in automotive applications like lighting systems. If one lamp fails, current continues to flow through the rest. In a series circuit, all would go out, which could be disastrous. Also, since all components connect directly to the battery terminals, the metal of the vehicle's body can become one of the conductors. One terminal of the battery and one of each component can be connected anywhere on the body or chassis to complete the circuit. This is called an earth or ground connection. It saves a lot of connecting wire. A feature of a parallel circuit is that the voltage across each component is the same as battery voltage. No matter how many components are added or removed, as long as they're in parallel, the voltage across them will be the same as across each other component, including the battery. Another feature of a parallel circuit is that the current flowing in each branch is determined by the resistance of that branch. For this circuit, the resistances of the bulbs are all equal, so the current flowing in each branch is the same. However, the sum of their individual currents is equal to the total current flowing in the circuit. When the resistances are not equal, then the current divides in accordance with the value of each resistance, but the total current flow is still the sum of the currents flowing in each branch. Another resistor of 12 ohms is now added to this circuit. It produces an effect which is the opposite of what might be expected. Current increases from 3 amperes to 4. This is because in a parallel circuit, adding more branches provides more pathways, but decreases the overall circuit resistance, so current flow increases. Total resistance of a parallel circuit is found by turning all the resistances upside down to make fractions called reciprocals. In this case, each 12 becomes 1/12. The 4 twelfths are added together, and the answer turned back up the way it was. 3 ohms is the total resistance in the circuit. Ohm's law confirms the ammeter reading of 4 amperes. Now, if 2 resistors are removed, what is the result? 1/12 plus 1/12 is 2 twelfths, which turned back the way it was is 12/2, or 6 ohms. Voltage across the components is still 12 volts, but by Ohm's law, the new current is 2 amperes. So removing the resistors in this circuit halves the current. This section examines series parallel circuits. One example of a series parallel circuit is this circuit for the panel lights. Here a rheostat is used to control the brightness of the bulbs. These circuits are analyzed using the laws applied to separate series or parallel circuits. This section examines electrical measurement. The ammeter measures the size of electrical current in amperes. Current flows through a circuit, so it must flow through the ammeter. That means connecting the ammeter in series by breaking into the circuit. The low resistance of the ammeter ensures that the circuit will operate normally when the ammeter is connected to the circuit. A voltmeter measures potential difference in volts across 2 points. It is connected in parallel. It has a high internal resistance, so as not to affect the potential difference across the component or circuit being tested. The ohmmeter measures resistance in ohms. The item to be tested must first be disconnected from its circuit. This is so any pressure in the circuit will not affect the readings of the meter. This section examines the battery. The wet cell lead-acid battery is the main storage device in automotive use. An automotive battery can supply very high discharge currents while maintaining a high voltage, useful for cold starting. It gives a high power output for its compact size, and it is rechargeable. This section examines capacitors. A capacitor can quickly store a small amount of electrical energy. It's then said to be charged. Inside are 2 surfaces, separated by insulating material. When the capacitor is charged, one surface is positively charged, the other is negative. When a circuit is closed between its terminals, the capacitor releases charge. It is then said to be discharged. A typical capacitor stores the charge on thin sheets of foil with sheets of insulation between them. These are rolled together to form a protective canister. This section examines conductors and insulators. Every substance, even air, will conduct an electrical current if enough voltage is applied to it. But the word conductor normally is used for materials that allow current flow with little resistance. The most common conductor is copper. It's used in virtually all the wiring that connects automotive components together. The heavier the current a conductor has to carry, the heavier the gauge or thickness of the wire. Materials that don't conduct current easily are insulators. The plastic covering on a wire and the ceramic portion of a spark plug are good insulators. This section examines the diode. A semiconductor diode has a single PN junction. If it is connected to a current source, with the P region connected to a negative pole and the N region to a positive pole, the holes will be attracted towards the negative pole and the electrons to the positive pole. This enlarges the depletion layer, which makes the insulated space larger, stopping current flow across the junction. If the current source is reversed, lots of holes flow across the junction towards the negative pole, and electrons travel in the opposite direction towards the positive pole. The PN junction floods with charge carriers. The depletion layer disappears, and with it the insulator effect. In this direction, the diode lets current flow. So using conventional current flow, a diode lets a low voltage current flow through it if current flows from its P side to its N side, but stops current flowing through it from its N side to its P side. This is a Zener diode. It is blocking current flow through it. But if the voltage of the current source is large enough, it can force current to flow through the diode. This is called breakdown. A Zener diode is designed to operate in this way. As breakdown voltage is reached, the Zener diode's resistance suddenly collapses. It lets a large current flow through it without damage. Because Zener diodes respond to certain voltage changes like switches, they are used in voltage regulators. Light-emitting diodes, or LEDs, emit light when they are connected in a forward direction. This section examines fuses and circuit breakers. They are designed to break the circuit if current flow is excessive. The most common kinds are fuses, fusible links, and circuit breakers. They are all rated in amperes. Their ratings are usually marked on them. Fuses are typically used in lighting and accessory circuits, where current flow is usually moderate. A fusible link is typically placed near the battery and, except for the starter motor, it carries the current needed to power an individual circuit or a range of circuits. Circuit breakers are not destroyed by excess current. A bimetallic strip heats up and bends, opening a set of contacts and breaking the circuit. In most types, as the strip cools, it resumes its original shape. The contacts close, completing the circuit once more. This section examines lamps. Modern vehicles use many different kinds and sizes of lamps. They all consist of one or more filaments which heat up until they glow. The filament material doesn't burn because most of the air in the bulb has been replaced by inert gases that stop combustion occurring. The power in watts is often marked on the lamp. The power in watts being consumed by the lamp is found by multiplying the voltage to the lamp by the current flowing through it. This section examines relays. Relays are switches that are turned on and off by a small electrical current. Inside a relay is an electromagnet. When a small current energizes this electromagnet, it attracts an armature blade and closes contact points. Current that the relay is designed to switch on or off can then flow across the points. As long as the small switching current flows to the relay, the much larger current will flow through its contact points. This section examines resistors. Resistors are so named because they resist current flowing through them. Putting a resistor in a circuit causes a drop in voltage across the resistor. So resistors are commonly used to control the voltage that reaches various components. It is also important to remember that each electrical component also has a resistance of its own. Most resistors that can carry large currents contain a coil of high resistance wire wound around a ceramic former to dissipate heat. Resistance is measured in ohms, represented by a Greek letter omega, and so resistors are rated in ohms as well, to indicate how strongly they will oppose any current flowing through them. Resistors also have a wattage rating. This is because resistors work by converting some of the electrical energy passing through them into heat. This section examines thermistors. Thermistors are semiconductor resistors. Their electrical resistance varies according to temperature. This makes them suitable for temperature measurement and for electronic control operations. Negative temperature coefficient resistors, also called NTC resistors, conduct current more readily when they are hot than when they are cold. NTC resistors are commonly used as part of temperature sensors in engine management systems. This section examines transistors and power transistors. These are semiconductor devices used as switches and to amplify currents. There are two kinds, NPN and PNP. The NPN transistor has a P-type semiconductor between two N-type semiconductors. A PNP transistor has an N-type between two P-types. Each of the three regions has a terminal. The center region is always called the base. The outer regions are the collector and the emitter. In the symbol, the emitter is the terminal with the arrow, always pointing to the negative material. In this circuit, this NPN transistor can act as a switch. If the control switch is open, the depletion layer at one PN junction is blocking current from flowing through the transistor and driving the load. With a closed control switch, a small current flows through the emitter base PN junction. The base has only a limited number of charge carriers, so extra ones flow across the emitter collector PN junction, letting current operate the load. The transistor then operates as a low-resistance conductor. A small current through the base lets larger current flow across the emitter collector junction. The transistor is then said to be turned on.